It's an honor to be part of this differential geometry conference. I'd like to talk about some new results in a very classical area, and in fact try to draw attention to some classical topics which are perhaps not as well known as they might be. So I'm going to discuss the volumes of moduli spaces in a very simple case. Moduli spaces of Riemann surface of genus 0 with n mark points. And the computation of the volume will be carried out using the Gauss Bonnet theorem for a class of sort of singular Riemannian manifolds that has been very little studied, although they occur in various forms throughout differential geometry. So this development was inspired by a beautiful paper of Kappas and Muller, which I will have very little time to go into the full detail of it, but I direct you to it. It's an amazing idea that they have. And it draws on work of Thurston on these moduli spaces. And for the proof of Gauss Bonnet, it turns on a paper of Allendorfer and Wey going back all the way to 1943. Okay, so let me tell you, but the story is much longer. These metrics on moduli space were really known to Schwartz and Picard, and they were studied by Deligne and Mostow, especially to construct some non-arithmetic groups, as I'll discuss later, and Cohen and Wolfart, Parker and Sauter computed some of the volumes I'm going to mention, and there are many others involved in this long history. Okay, so what are the mathematical goals? I want to calculate the volume of moduli space in its complex hyperbolic metric, which I will describe. And the method is to compute the Euler characteristic of the completion of this moduli space, which will turn out to be a cone manifold, and then apply Gauss Bonnet. And as an application, these volumes yield new and useful invariants of non-arithmetic subgroups in SUN1. So that's the plan. So first, let me start with some very traditional questions. So let's talk about the ordinary Euler characteristic of moduli space first. So first, what is moduli space? It's the space of n tuples of distinct points on the Riemann sphere. They are given an ordering. You're not allowed to permute them. But we do mod out by the action of the Riemann sphere, and the result is a manifold, not an orbifold. How do you compute its Euler characteristic? Well, it's a fibration. If you fix n minus 1 points, then the nth point ranges in the complement of the n minus 1 points, which is just a sphere with n minus 1 points removed. And so you have a fibration of the type described here, and so the Euler characteristic of the m minus 1 punctured sphere is minus n minus 3, and so you by induction, you see that the Euler characteristic of moduli space up to a sign is just n minus 3 factorial. Okay, so the traditional Euler characteristic is exceedingly easy to compute. Less commonly computed, but certainly well known, are the Euler characteristics of the Deligne-Mumford compactifications of moduli space. So this sequence, 1 minus 1, 2, minus 6, 24, I think you can guess how to continue. This sequence is probably less familiar. Those are the Euler characteristics of the compactifications. Let me just do one example, just to show you some diagonals, as in not totally unrelated to Claire-Voisin-Stock. So how do you construct this moduli space for 5 points? Well, you can assume the first 3 points are 0, 1, and infinity. That gets rid of the action of the Mobius group. And then the remaining 2 points have to be chosen on P1 cross P1, but they have to avoid each other, so they can't be on this diagonal. And they have to avoid 0, 1, and infinity, which creates 6 more lines. And the complement of these 6 lines is the moduli space of 5 tuples of points on the sphere. It's a 2-dimensional surface, quasi-projective, and its Euler characteristic is easily computed. We removed 7 lines, but that took out too many points, so we had 12 back in, and we get an Euler characteristic of 2. As for the compactified moduli space, the Deligne-Mumford compactification records when points collide, it records the asymptotic shape of these configuration of points. And in this picture, at these triple intersections, you can form a local cross ratio. You have 3 points shrinking to nothing, and they span a triangle of a certain shape. You should record the shape of that triangle, and to do so, you need to blow up these 3 points. So that adds 3 P1s to P1 cross P1, and then you have to remove the 3 points you blew up, and that gives the Euler characteristic of 7 for the compactified moduli space. And it's a beautiful fact that was discovered by Ezra Getzler that, in fact, these two types of Euler characteristics fit together into an elegant formula. Namely, if you take this generating function for the traditional moduli spaces pre-compactification, and you form the corresponding generating function for the compactified moduli spaces, then these power series are inverses of one another in the sense that the composition of f with g is the identity. And that allows one to recursively compute, for example, these Euler characteristics here. And actually, I wrote a short note giving a very elementary proof of this. Getzler's proof is couched in some quite sophisticated discussion of operads, et cetera. But in fact, there's an elementary proof that can be done using the enumeration of what are called stable trees, trees where the internal nodes have at least degree 3. And in fact, it turns out that not only does this particular formula hold, but the configuration of strata of moduli space gives the universal formula for the inversion of an arbitrary power series. And so it's quite amazing that that combinatorics of that rather complicated operation of inverting a power series as a function is encoded exactly by these strata. Okay. Now that I have these Euler characteristics, let me try to compute some volumes. Well, what kind of metric am I going to put on moduli space? Certainly, it should be compatible with a complex structure. However, in fact, the metric will be a complex hyperbolic metric. But that seems strange to anyone who works on moduli space for the following reason. It's well known that moduli space is not anything like a symmetric space. In fact, it's totally inhomogeneous as a complex manifold. So here's a theorem of Royden. If you take the universal cover of moduli space, its automorphism group is discrete. It's not a Lie group. And in fact, people have drawn pictures of it, and it has a fractal boundary under its natural Bayes embedding. This is, of course, for more than 4 points. For 4 points, of course, the universal cover is the hyperbolic plane. That's misleading. In higher dimensions, it's nothing like a symmetric space. So the universal cover looks nothing like complex hyperbolic space. Complex hyperbolic space is just a ball sitting in, this should be n-3, sitting, it's just a ball in the unit Euclidean ball in affine space Cn. And so moduli space is not a quotient of complex hyperbolic space for n bigger than 4. Okay, well, let's set that aside for the moment, and I want to turn to another face of moduli space, how one can think about the configurations of n tuples of points on the sphere. And this is the idea of thinking of M0n as a moduli space of polyhedra. In addition to the points on the sphere, we're going to fix some weights, mu1 up to mu(n). Each weight will be between 0 and 1, and the sum of the weights will be equal to 2. And then when you have a configuration of points, these b sub i's, you have n points on the sphere, you can form this weighted combination of them. And this is a divisor of degree 2. It looks like it's formally a section of the anti-canonical bundle on a divisor for the anti-canonical bundle on on this surface, or minus, sorry, there should be a minus sign in here for a canonical divisor. And in fact, there's a holomorphic one form you can write down with poles at exactly these bi's. You just take the obvious rational function that has a pole of order mu I at x minus bi. The only problem is that, of course, this fractional power of x minus bi is a multi-valued function. And that's where the whole theory of hypergeometric functions enters this discussion, and there's a lot of interesting things to say there. It becomes very technical and ungeometric, though. But we can rectify that multi-valuedness of this one form by simply taking its absolute value. The absolute value makes perfect sense, is not a multi-valued function, and it gives you a metric on the sphere. And our constraint that these mu i's are between 0 and 1 means that this metric has positive curvature at the poles of omega, and is flat everywhere else, because the absolute value of a one form that's non-vanishing gives you a flat metric on a Riemann surface. So in fact, a configuration of points together with these fixed weights determines a convex polyhedron in R3. That is, it's well known by Minkowski that this positively curved sphere can be isometrically embedded into R3, and it's just a polyhedron with vertices at the bi's, and the angles at those vertices are determined by these mu i's. These are the so-called cone angles. So let me give you an example. If we want to study the moduli space of 12 points on the sphere, why not make all of the weights equal to 1/6? That certainly sums to 2. And a particularly nice element of moduli space can now be visualized as the dodecahedron. So the 12 points are the 12 vertices of the dodecahedron, and there's a small angle defect. The surface is not quite flat here intrinsically. The total angle around this point is not 2 pi, but 2 pi times 5/6. And as the points move on the sphere, we get families of polyhedra which are combinatorially dodecahedra, but of course not regular for general configurations of points. So this is the same moduli space, but it's a different way of thinking about it. It's thinking about it as parameterizing these polyhedra. And in fact, sorry? Then the angles, then you get a polyhedron where the angles are not equal. I'm going to consider that case later. There are certainly plenty of polyhedra that don't have the same angles at their vertices. So right at now, so far, the M012 is not changing. There's a way to take M012 plus these weights and associate a polyhedron to every point in the space, okay? But M012 has not changed. It's the same M012 as it was on the last slide, okay? It doesn't depend on the mu I. There is something, though, that will depend on the mu I, and that is the metric I'm going to put on M012. So what I want to say is that when you start thinking from moduli space from this perspective, what you discover is that these moduli spaces are complex hyperbolic after all. So I'm going to denote by M0 and mu the moduli space of cone metrics on S2 with the given angles, but in fact that's the same as this original moduli space. And the theorem is that this space carries a natural structure of a complex hyperbolic manifold. In other words, it's locally modeled on complex hyperbolic space via the periods of the associated one form, which are very similar to saying the lengths of the polyhedron that was just presented. And this theorem has a long history. Various incarnations of it are due to Schwarz, Picard, Deline-Mosto, et cetera. But one of my most amazing mathematical experiences in my life is in 1986. Thurston started discussing a math Olympiad problem in his class. There was a famous math Olympiad problem about 5 people sitting around a table. Some are in debt, some have money. You can think of them as the European nations. And one of them borrows the exact amount they're in debt from their two neighbors. Then their debt becomes a surplus, but then their two neighbors might go into debt. And you keep repeating this process. And the Olympiad question was, does this ever terminate? Does it depend on the number of steps, depend on how you try to balance the budget, et cetera? And starting from this Olympiad problem, Thurston reinvented and generalized all of these theorems about cone manifolds. So it's sort of implicit in very elementary considerations, namely a sort of geometric proof of this Olympiad problem. Okay, so what's the catch? I'll tell you the catch before I continue. Of course, this seems to contradict my previous result, that moduli space is not a quotient of complex hyperbolic space. And the catch is that the metric is not complete. It's natural, but it's not complete. So let me give you one example of this metric, of what the metric is, which is particularly easy to describe and shows a really nice relationship between this discussion and Hodge theory. So I'm going to consider the weights where the denominator is 18 and the weights are 4 7s and 1 8. So this is the moduli space of 5 points on the sphere. But we can always assume that this 8 point is at infinity, and then the 7 points are in the finite plane. Now, so really we have 4 points in the finite plane plus the point at infinity. So there's a natural map from this moduli space to the moduli space of Riemann surfaces of genus 25, given by taking a sort of generalized hyperelliptic equation. So we take x1, the polynomial with zeros at b1 minus b4. We let y to the 18th equals this, and that defines an algebraic curve whose completion is a compact curve of genus 25. Now, what am I going to do with this curve? Well, one thing we notice is that since I took an 18-fold branch cover, there's an action of z mod 18 on the first homology of this surface. And we can decompose the first cohomology into eigenspaces. The eigenspaces will be indexed by 18th roots of unity. And there's also a very natural holomorphic one form on this Riemann surface. Namely, it's given by dx over y to the 7th. That generalizes the form dx over y that you might write down on a hyperelliptic curve. And that form lies in the eigenspace for zeta, the primitive 18th root of unity to the minus 7th power. Why? Well, the action of z mod 18 is by multiplying y by zeta to the zeta 18. And when you do that, since it's in the denominator, this form multiplies by the minus 7th power of that root of unity. Now, this cohomological subspace in which the one form resides, the cohomology class sits in H1 of xq. H1 of xq is actually defined topologically. If you take a branch covering, you have these deck transformations, you decompose the cohomology, there's no complex structure involved. So there's a locally constant way to split the cohomology up, and then you take the intersection form on cohomology and restrict it to each of these invariant subspaces, and it has a certain signature. The intersection form, the Hermitian form on the whole cohomology has signature GG, where G is 25, and there's a nice mnemonic to compute its signature on each of these pieces of the cohomologies. So here's the mnemonic. We want to do 718. Let's just forget about the minus sign. What we do is we say, well, we're doing 4 points in the plane, right, B1 up to B4. So we mark 4 points equally spaced around the circle. And then we draw the line from 1 to the 7/18th root of unity. And then we count the number of green points above the line and the number of green points below the line, and that gives the signature of the quadratic form on this space. That's just a nice way to do it. One can easily verify that this is correct, that this is a way to visualize it. So you'll notice that this signature is the signature of a Lorentz form, a complex Lorentz form. In other words, it's the signature of the type of form that we use to construct complex hyperbolic two-space. And you see, since for each configuration of points we get a canonical cohomology class, namely this cohomology class coming from the 1 form, we get a point in the space of lines in this Hermitian space. And the space of lines in that Hermitian space that are positive, that is, have positive self-intersection number, that's the integral of omega wedge omega bar times I over 2 is positive. The space of positive lines in this Lorentz space is nothing more than complex hyperbolic space. That's the Minkowski model for complex hyperbolic space. And so we have now defined a map from configurations of 5 points into CH2. And this map can be proved to be an immersion. And so we just pull back the metric, and all of the choices here were canonical, so these pulled back metrics fit together and give a complex hyperbolic metric on the entire moduli space. And by the way, of course, as you go around in the fundamental, if you follow a loop around moduli space, this vector space is locally well-defined. It gives a flat vector bundle over moduli space, but it has non-trivial monodromy. The monodromy preserves the inner product of signature 1, 2, and so you get a representation of the Bray group into U1, 2, which turns out to be a specialization of the well-known Barrow representation. So in fact, these kinds of representations of the Bray group were at least implicitly known long before Barrow to people who studied hypergeometric functions. Okay, so now we have our moduli space, and we have a metric on it. The metric depends on these weights, mu I, and I can ask what's the volume, and here's the answer. This was the question that motivated the whole discussion that the whole ensuing discussion. So here's the answer. So the volume of moduli space in this metric coming from these mu's is, well, it's given by this formula, and you'll understand this formula better as we go along, but let me just say that it's a sum over partitions of the indexes from 1 up to n. These are the labels of our points into blocks B. And then for each such partition, you have to form a product over the blocks of a certain function here, and you see there's sort of an angle defect entering. But you'll notice that the angle defect is raised to the power of the size of the block minus 1. So it's only blocks consisting of 2 or more points that even contribute to this product here. And the constant that appears in front is the constant that would appear in front of the Gauss Bonnet formula for a complex hyperbolic manifold. And then this term is analogous to the Euler characteristic. So if this were a complex hyperbolic manifold and this were its Euler characteristic, then this would reduce to that formula. Okay, so special cases of this formula, written down in very different ways, were computed by Parker and Sauter for certain low-dimensional examples of these moduli spaces, namely the cases of 5 and various cases of 5 and 6 points. Certain inequalities had to hold on the mu i's and so on. And that was done by finding explicit fundamental domains for the action of the group. So I want to exploit a different method to compute the volume. I'm going to exploit this beautiful theorem of Thurston, and this is something that Thurston really added to the theory that was not present even all the way up through the work of Deligne and Mostow. So what Thurston showed is that the metric completion of M0 and mu is a complex hyperbolic cone manifold. And by the way, the mu i's are allowed to have real values. In the work of Deligne and Mostow and everyone prior, the mu i's were only taking rational values. And this statement works for all mu i's under consideration. Okay, so I want to say a couple of words about what a cone manifold is, and I think as far as I know, the first truly general definition of a cone manifold appears in this paper of Thurston's. But many special cases of cone manifolds have appeared before. So let me tell you the idea of a cone manifold. Take a bunch of spherical polyhedra, say subdomains of the 3-sphere. Now, by polyhedra, I mean they should have totally geodesic faces, the edges should be geodesics, and so on. But of course, they're spherical, so they sort of bend out. Their intrinsic curvature is positive. That's why I've drawn them as being slightly puffy. And then you glue them together in any way you like under isometrically paired, under a pairing between faces that are isometric to one another. So you glue them together in any way you like. And that's an example of a cone manifold, a very special type of cone manifold, but an example nevertheless. And so what I want you to notice is that along the edges, the total angle may not add up to 2 pi. But it's even worse. The length of a vertex may be an object which looks very different from a sphere. It's just something built out of spherical polyhedra of dimension 1 less. So the length of a vertex might be some sort of spherical cone structure on a surface of genus 3. So what's been considered very frequently in differential geometry are cone manifolds which have a singularity along a codimension 2 locus, and there they just have a certain constant angle. But in a general cone manifold, there's a whole stratification of singular loci such as can occur in this construction. Okay, so I have to say that as soon as I got the idea of computing these volumes using Gauss Bonnet, I was able to compute the right-hand side of this equation, and I presumed that the Gauss Bonnet formula was known, and I sent Capes and Miller the formula for the volume the next day. And then I spent a year proving the cone manifold version of Gauss Bonnet, because it turned out it's not in the literature, and I realize now I shouldn't have expected it to be, because there's no literature on the general theory of cone manifolds at all. But the formula is extremely simple. So remember, we're interested in the volume of moduli space. The volume can be computed by integrating over the top dimensional stratum, which is smooth. And so quite generally, if you have a compact cone manifold, a Riemannian cone manifold, it has on its top dimensional stratum, which I've written as m brackets n, the usual Gauss Bonnet integrand, which you integrate with respect to volume. That's the right-hand side of the equation. And then the left-hand side of the equation is the Euler characteristic of this cone manifold. And the Euler characteristic is computed as follows. Well, it turns out that each stratum is a totally geodesic submanifold within the entire cone manifold with respect to its path metric. So I'm using m super sigma now to index the strata, the individual connected pieces of the strata. And along each connected piece, there's a normal cone. And this normal bundle has a total solid angle. The unit normals to a point on one of these stratum form a spherical cone manifold, and you can compute its total solid angle and take its ratio to the solid angle of a sphere of the same dimension. And so this is the solid angle normalized to be 1 in the case of an actual submanifold as opposed to a manifold along which there's some singularity. And so we take a weighted sum of the simplices and we get the volume. Okay, now this formula is very easy to guess. And in fact, some instances of it are well known. Certainly the case of an ordinary manifold. This reduces to ordinary Gauss Bonnet. But it's also another way to get cone manifolds is to look at orbifolds. In the case of orbifolds, these solid angles will all be of the form 1 over n, where n is the order of some group that's locally defining the orbifold. And this formula is due to Satake. Okay, so with this formula in hand, though, if you posit this formula, then which, by the way, let me just say again what it is. It's just the sum over the connected strata of the Euler characteristic times the solid normal angle. If you have this formula in hand, then it's pretty easy to prove the formula I gave before. So this constant having to do with the fact that we're in complex hyperbolic space times the volume is equal to this generalized Euler characteristic. And here's the formula for the generalized Euler characteristic. And the first piece, you'll notice, has the number of points in the partition minus 3. So what's happening? We have the moduli space of n points. At one of the boundary strata, these points are colliding. And when they collide, 1, 2, 3 maybe collide together. Then the subset 1, 2, 3 is one of the blocks of our partition. So the partitions are describing the ways that different vertices can collide. And then this is the Euler characteristic of the moduli space of configurations of points after collision, which we computed just at the very beginning of the talk. And then this second part here, this is a product of angle defects, and it's not hard to believe that this is giving the solid normal angle that's in the formula here. Okay, yes? Yes? No, it changes continuously with the mu's because the mu's are here. Right? Yeah. Okay. So just to give an example, so one thing I should point out though is that there's no contribution to the sum unless each block of the stratum has a weight less than 1. So there's a sort of stability condition. That is, when the points collide, so remember the denominator here was 18, so when the points collide, the total weight should still sum to less than 18. So 7 and 7 can collide to form a vertex of weight 14, but you can't have 3 of these vertices to collide. And in fact, the fact that you can't get 3 to collide is very similar, is just the statement that the angle would be wrong. You see, these two vertices have to be able to converge to something that still has a positive angle. So it's obvious from the picture that you can't force 3 consecutive vertices here to collide. And geometrically, this just means we keep the curvature positive in the limits. And one can also view this as a stability condition. And in fact, Brendan Hassett has considered these moduli spaces, these compactifications of M0n prior to this, just from the standpoint of stability. Okay, so with this formula in hand, I can say the following. So what did Deligne and Mostow do? Well, for each of these weights, mu I, you get this incomplete complex hyperbolic object. Maybe, if you're lucky, its metric completion is an orbifold. If so, then its universal cover is the complete complex hyperbolic space, and you get a lattice in SUN1. And so Deligne and Mostow found all the values of the mu I that give rise to orbifolds. And it turns out there are only 94, well, that's pretty many, but there's a finite number that give rise to orbifolds as opposed to honest cone manifolds. And we now know the volume of all of these Deligne-Mostow examples by an immediate application of this formula. Okay, so let me say just a word about the proof of Gauss Bonnet. So it uses the polyhedral Gauss Bonnet theorem that was proved in 1943 by Allendorfer and Weil. So let me say a few words about this formula. So their formula, they consider what they call a Riemannian polyhedron of dimension n. This is something that locally looks like an honest Euclidean polyhedron up to diffeomorphism, and it has a Riemannian metric that extends smoothly up to the boundary of this polyhedron. That's the local model. And they have a formula for computing the Euler characteristic in terms of an integral over the inside of the manifold plus an integral over each facet of the boundary. So you should think of applying this to an actual polyhedron with curvilinear faces and edges, say sitting in R3. That's the kind of thing that's covered by this formula. And I have to tell you what the integrands are. So the first term here are Rijk. L is the Riemann curvature tensor. The first term here is, of course, the standard Gauss Bonnet integrand. But these other terms, these integrals over the boundary strata, they are not just integrated over the boundary strata, but they're also integrated over the set of external angles along each stratum. And I'll describe what that is in a moment with a picture. And so along these strata, you integrate not just over x, but also over part of the normal bundle to the stratum. And so you integrate something that depends on both the point and a direction into the ambient space. So this part is what I call the intrinsic curvature, and the second part, which is this complicated expression, I call the extrinsic curvature, extrinsic Gauss Bonnet integrand, really. And what you see is this now involves not just the Riemann curvature tensor, but also the second fundamental form, as you would expect. The way in which these facets of the polygon are extrinsically curved also enters into the Gauss Bonnet formula. So let me just say a word about this beautiful formula. First, this formula has not been very much used in differential geometry. Why did they prove it? They proved it because Allendorfer and Fenchel had just proved Gauss Bonnet for arbitrary compact manifolds that can be isometrically embedded in Euclidean space. And I'll say how they did that. But at that time, the Nash embedding theorem, which they could have applied then to deduce the general case, was not known. What was known is a local embedding theorem. But if you have a Gauss Bonnet theorem for polyhedra, then you can take your arbitrary manifold, cut it into pieces that admit local embeddings, apply Gauss Bonnet to all of the pieces, and add things up, and then you get Gauss Bonnet for an abstract manifold, even though you don't know that the abstract manifold can be embedded. And this is exactly what Allendorfer and Bay did, and I think that was their motivation, to deduce the general Gauss Bonnet theorem. And one of the reasons I think this is not very well known is that it was immediately superseded, that is the next year, by Chern's intrinsic proof of Gauss Bonnet, which has nothing to do with embeddings in Euclidean space at all, and is a completely slick differential geometric discussion behind it. And that's one reason. Another reason is the whole notion of a Riemannian polyhedron, as Vey notes, is not very well founded. There's lots of different definitions that slightly diverge, and this whole topic is not very well developed at all. And it's not needed if you work on closed manifolds or manifolds with boundary. Let me just say a word about the proof. The proof comes from Weil's tube formula, which had been proved in 1939. The idea is you put your polyhedron into a Euclidean space isometrically, and then you form a tube around it. And each point, this is just the points at a constant distance from the polyhedron, and constant distance epsilon, let's say. And at least for epsilon small, each point on the boundary of the tube has a unique nearest point on the polyhedron. And how big, and then we can also apply the Gauss map to the tube as well, and we get some angular region swept out on the sphere. So how big is the angular region corresponding to this vertex of the polyhedron? Well, you'll notice its size is not determined by the inner angle of the polyhedron. That is, as the inner angle gets smaller, this outer angle, which is sort of an external angle, gets bigger. And so you don't use the inner angles, you use the outer angles in the Allendorfer and Bay formula. And with that in mind, the formula is not too technical to deduce from Weil's tube formula. And in fact, the idea of using the tube formula was this is exactly the way the proof of Allendorfer and Fenchel went. So it uses this picture. Okay, so what is suggested by this kind of discussion is if you have a cone manifold, you can cut it into Riemannian polyhedra. That's the great advantage of polyhedra is you can go right down to the cone locus and cut along the cone locus. You don't have to take neighborhoods of it and take a limit and so on. You can actually dissect your manifold into Riemannian polyhedra, just as you can for the spherical cone manifold I discussed earlier. So why isn't it more or less trivial then to deduce Gauss Bonnet from Allendorf-Hervé? There's two challenges. One challenge is that it's the inner angles rather than the outer angles that intervene in the formula. So when you're forming the total solid angle around this point, that's the sum of the inner angles for all the cells to which it belongs. But the integrals involve these outer angles. So there's some complicated recursive way to transport information from outer angles to inner angles in spherical geometry that has to be brought into play in the discussion. The second challenge, which is already evident in the complex hyperbolic case, is the following. You might not be able to cut your space into polyhedra with totally geodesic faces. The spherical case is very misleading, and the complex hyperbolic case is a good example. If you have a complex hyperbolic manifold, it has no odd-dimensional, totally geodesic submanifolds, except, of course, for dimension 1. So if you can't build cells that have totally geodesic boundaries. So the most naive picture of how this argument is going to work just is impossible. It works very nicely in the real hyperbolic case, because there you could decompose into honest polyhedra. So what happens is you have this pristine hyperbolic cone manifold, but you are forced to cut it along these odd-dimensional wobbly faces, and then the second fundamental form and all those extra terms enter. And then you have to reassemble those pieces and show that those new forms, which you didn't want to have and you sort of arbitrarily introduced, reassemble to cancel out and give the slick formula that we discussed earlier. OK, so that's just a hint of how Allendorf-Hervé is used to deduce Gauss Bonnet. OK, so finally we come to the motivation for computing these volumes. So as I mentioned, this was all inspired by a beautiful paper of Allendorf-Hervé, of Capes and Müller in 2012. And what they were doing is they were computing new invariants for non-arithmetic subgroups of SUN1. So let me say a word about why one is interested in this. So according to Margulis, if you have a lattice in a higher rank, say semi-simple Lie group, it's arithmetic. But of course, if you have a lattice in SON1, that is, if you have a real hyperbolic manifold, it might be arithmetic, it might be not. For example, in dimension 3, most hyperbolic 3 manifolds are not arithmetic. So lattices in rank 1 spaces don't have to be, and usually are not, arithmetic. However, as you go from the reals to the complex, to the quaternions, to the octonions, you tend to acquire Margulis superrigidity even in rank 1. So in fact, there are only finitely many commensurability classes of non-arithmetic lattices known in SUN1. That is, there's roughly speaking only finitely many types of non-arithmetic complex hyperbolic manifolds of finite volume known, and in fact, they're only known in dimensions 2 and 3. And even when you find them, it's hard to know if you've actually found a new example, because the example you found might be a covering of an example somebody else found. Or these two examples might have a common covering space of finite degree. In other words, the two groups might just be commensurable, which is not surprising. Once you find one non-arithmetic group, any group commensurable to it is also non-arithmetic. So it's nice to have new invariants of non-arithmetic groups to distinguish them. And in fact, these weights that I chose here give rise to a non-arithmetic group in SU21. So let me say a little bit about what the underlying picture is. So we have these weights, and we saw they determine a form of signature 1, 2, some sort of complex hyperbolic structure on moduli space. Now, this whole discussion depended on the choice of an 18th root of unity, which means that the group we get in SU1, 2 is also defined over a number field, namely this cyclotomic field. And so we can change the root of unity using the action of the Galois group. And if we change the root this to the -5th root of unity, it turns out that what that does is it changes the weights from the weights here to the weights here. So we get, in fact, a new system of weights. And since 5/18 still cuts these green points into 1 above and 2 below, this new set of weights gives, again, a complex hyperbolic structure on the same moduli space, the moduli space of 5 tuples of points on the sphere. Okay, so we have 2 Galois conjugate metrics on the same moduli space. And what Deline Mostow observed is that in this example and a few others, the object we started with actually gave rise to an orbifold. So an orbifold will give a lattice in SU1, 2, because it has a finite cover, which is a manifold, and then the manifold gives rise to a lattice. And for example, to test whether or not this is an orbifold, you have to look at some of these potential collisions, and it turns out that the cone angle along this stratum resulting from this collision will be 1/9, and the fact that that's 1 over an integer is necessary for the cone manifold to be an orbifold. And in fact, all those tests are passed, and in fact, we do get an orbifold. Now, on the other side, the same collision can occur, but it gives 2/9. So this side gives an honest cone manifold, not an orbifold. So how are these two objects related? Well, so as I just said, on this side, we get a metric, and the metric completion is an orbifold, and it's beautiful. It's the complex hyperbolic space modulo a lattice. On this side, we have new weights. The metric completion is a cone manifold, and it's not covered by complex hyperbolic space, but it has a holonomy group coming from the developing map to complex hyperbolic space, which I'll call gamma prime. Gamma prime is just the Galois conjugate of gamma. That's right. No, whether or not it's an orbifold depends on the choice of metric. It's not a property of the complex manifold. If you have the sphere with 2 marked points, you can put whatever cone angle you want at those marked points. If the cone angle is of the form 2 pi over n, it becomes an orbifold. If it's not of the form 2 pi over n, it's not an orbifold, but you haven't changed the underlying space. But you make a good point, which is that these 2 moduli spaces as complex manifolds, as complex varieties, depend only on certain inequalities between the mu's, not their exact values. So what happens in this case is, let's think about it. We have moduli space itself embedded as a dense subset of both of these completions. And in fact, because this side is an orbifold, this correspondence, this homeomorphism between open dense sets, extends to a holomorphic map from this moduli space to this moduli space. And so when we have a non-arithmetic lattice, as in this example, what we get is a holomorphic map that implements the Galois conjugacy from gamma to gamma prime. See, this induces a map on pi 1 of the 2 sides. It induces a map on their holonomy of their complex hyperbolic structures. So you get a map from this discrete group to its Galois conjugate group. And this Galois conjugate group is dense in U1, 2. As one can easily verify, it also follows from Mostow rigidity that it has to be dense. And that's the characteristic feature of a non-arithmetic group, that when you take in an arithmetic group, what usually happens is you have a subgroup of SU1, 2, and its conjugates all live in the compact group SU3. And so the projection from that big product to the single non-compact factor gives you an arithmetic lattice. Here, the group embeds into the product of two copies of SU12, and its projection to one factor is dense, the other factor is discrete. It's a non-arithmetic lattice in SU12 for that reason. Okay, so what we see is that if you look just from the point of view of algebra, you have these two isomorphic groups, one discrete and one dense. But if you look from the point of view of geometry, you see this Galois conjugacy is just a shadow of this much richer structure of these two compactifications and this holomorphic map between them. In any case, how can you use this to get an invariant of non-arithmetic groups? Well, this map, it turns out to be a contraction by the Schwarz lemma. And so one invariant you can do is you can compute the ratio between the volume of the original orbifold and the volume of its Galois conjugate cone manifold. And this ratio is an invariant of the commensurability class of gamma. That's what Capes and Muller showed, that if you pass to subgroups of finite index, in fact, these kinds of invariants are preserved. In this case, it's actually pretty easy to see, because when you pass to a subgroup of finite index, you take finite degree covers of the top and bottom. They both multiply by the degree, and so the invariant remains the same. Okay, so this is an invariant that can be attached to non-arithmetic groups, and only non-arithmetic groups. But it can be used to complete the proof of the following theorem. This was first proved by Capes and Muller, that the 16 non-arithmetic lattices, which were found by Delinen and Mostow, arising from moduli spaces, they fall into exactly 10 commensurability classes. And in fact, this invariant is very good at detecting commensurability classes. Here's the table of the non-arithmetic examples, and here's their corresponding invariants. And if you were to identify, everything that looks like it might be Galois conjugate, to be commensurable, you have to have the same invariance on this side. Everything that looks like it might be commensurable is commensurable, with one exception. This group here is not commensurable to the two groups under it. So there's 9 different volume invariants that appear, and there's exactly 10 commensurability classes. And in fact, you can polish off the problem very easily, because the trace fields of these two groups here are the same, and they differ from the trace field of this example. Okay, so that's telling the story backwards. It was to ratify this table that I found it interesting to study the theory of cone manifolds and use Allendorfer-Bay to leverage a version of Gauss Bonnet in that setting. Let me conclude by showing you one picture of everything that's going on in the one dimension where you can visualize it. So it would be nice if we could draw polyhedra in complex hyperbolic 2 space, and some people do that. I don't know how to do it, and I don't understand what their pictures mean. But I do know how to deal with complex hyperbolic 1 space. And indeed, this whole theory works perfectly well for the moduli space of 4 points on the sphere. So let me give you an example of a non-arithmetic group in SL2R, that is in an ordinary non-arithmetic Fuchsian group. So this comes from the following pair of Galois conjugate weights on a 4-tuple of points, and it gives rise to the following 2 beautiful groups. On this side, you take a regular hyperbolic pentagon, and you take the group generated by reflections in its sides. That's discrete. And maybe you add in the rotation by order 5 and as an obvious additional symmetry. Here, you take reflections in the sides of an ideal star. That's certainly not discrete. However, there is a natural conformal map with a branch point at the center here that maps the pentagon to the star, sending edges to edges. And that map can be developed by Schwarz reflection to give a map of the whole disk to the whole disk. And it clearly then conjugates the group gamma to the group gamma prime. So this is an example of one of these holomorphic maps, now pulled back to the universal cover, which implements this Galois conjugation here. And by the way, all we're doing is we're taking this 5th root of unity here, which is 1/5 of the way around the circle, and conjugating it to this fifth root of unity here, which is 2/5 of the way around the circle. That's how you turn the pentagon into the star. And this map arises, as I said, from T04 and gives a representation of the Bray group on 3 letters, etc. But let's just say what the quotient cone manifolds are, because they're very, very simple. So the quotient cone manifold here is the following orbifold structure on the sphere. There's actually a cusp, and then there's an orbifold point of order 5 and an orbifold point of order 2. So it's a traditional triangle group of classical type. Here what happens is when you Galois conjugate, the angle here, the orbifold number, changes to 5/2. So it's as if the angle here is double what it was here. It's as if there should be a group of order 5/2 corresponding this point, which of course there isn't, and that's why this is a proper cone manifold. And if you compute the Euler characteristics on both sides, you see that this cone manifold has 1/3 the volume of that one. So that's the value of the invariant. Now, in fact, this picture has been around for a very long time, about 10 years. You see, if you take the graph of the identity in F, you get a curve sitting in the product of the hyperbolic plane with itself. And the group gamma, or the group gamma prime, they embed into SL2 of Z adjoin the fifth root of unity. And so, in fact, this picture gives rise to a curve on a Hilbert modular surface. That Hilbert modular surface embeds into the moduli space of Riemann surfaces of genus 2, and it turns out that this curve has the beautiful property that it's isometrically embedded from the hyperbolic metric to the Teichmüller metric. And these curves are very rare and have been intensely studied of late. It's closely related to the work of Eskin and Mirzakhani, and they're still not all classified. But what I want to draw your attention to is that this picture, which emerges for any non-arithmetic group, gave rise to these very interesting and subtle examples in Teichmüller theory. The other non-arithmetic groups give higher dimensional versions of this picture. And we don't know, there's something therefore like higher dimensional Teichmüller curves. We don't know how they fit into a more general moduli problem, but the connection, I think, is very intriguing. Okay, I'll stop there. Okay, so the question was, if you take a quadratic differential on the sphere, which, by the way, is necessarily meromorphic, then it gives a cone manifold structure to the sphere, and does that somehow fit into this discussion? And it does, but you see, in the first simplest case is a quadratic differential with simple poles at 4 points. And then you just get the weights of 1/2 at each of these points, or 2, 2, 2, 2, 2 with denominator 4, and it fits perfectly into this space. And of course, it's just secretly the moduli space of elliptic curves being described in its usual way. What if you take a quadratic differential with 5 poles? Well, then it has to have 1, 0. And at that 0, rather than having positive curvature, you have negative curvature. So it's not a special instance of what we've been discussing, because we had to have these mu i's between 0 and 1. And in fact, that played a critical role in the fact that the form that we got at the end had signature n1, that we got complex hyperbolic space. And so what happens if you try to mimic this story is you do indeed get a geometric structure on the moduli space of n points, but it is not coming from a Riemannian metric, it's coming from a Lorentz metric, or more generally a metric of signature PQ. So the negative curvature gives rise to this indefinite metric, which could definitely be investigated and should be looked at. By the way, there's representations of the Bray group into SUPQ that arise in this way very naturally and have only recently began to be understood. Say it again. Oh, okay. That would be great. So the question was, so the moduli space has the structure of an algebraic variety. It's a different compactification from the Deligne-Mumford compactification. And the question was, is there a way to turn the volume calculation into a calculation involving tautological bundles over Brendan-Hassett space? And I don't know how to do that, but remember that real values of mu I must enter somehow. So you would sort of have fractional powers of line bundles or something like this.